Hey, welcome back to Famama Physics! In these videos, we're going to talk about conservation of momentum and lots of collisions. Before we dive into examples, I just want to quickly go over the key things I want you to know about conservation of momentum. So, let's get the show on the road. We know, I've talked about before that in this unit, we have gone over momentum, impulse, now conservation of momentum. I also mentioned that these three topics will actually just be Newton's three laws in disguise. And we will actually go over that in this video today. I'm going to show you that. But before that, let's talk about the definition of conservation of momentum. And again, I have to emphasize, just like conservation of energy, a lot of textbooks, online resources will tend to get the definition. It's a very small little subtlety. It will tend to mix up the word conserved with the word constant. Okay, so I will talk about why that is right now. Okay, now we've learned that when there is a net external force acting on the system, our momentum changes. So imagine there's like an average force applied over some amount of time, leading to a change in momentum, which is our impulse. Okay, our momentum changes in our system. So let's say this is my system, and at the boundary, let's say there is an exchange of forces or whatnot. Then as a result, my system will have a change in momentum. You might think that in this case, momentum might not be conserved, but let's just be very careful. In this particular case, my momentum in my system does not stay constant, but that doesn't mean my momentum is not conserved, okay? So be very careful. And the reason why is because there was an exchange with forces, external forces outside of my system, which resulted in my momentum in my system to change. So we can still track the momentum. We understand where that momentum comes from. It doesn't just come out of thin air, okay? So that's why we still say the momentum is conserved. It's not constant, it's still conserved. And you can think of conserved meaning trackable momentum, something that we can model in our solutions, okay? But then oftentimes when we deal with problems in our textbooks, as well as oftentimes when you're forced to say regurgitate the definition of conservation momentum on an exam, such as your IB exam, we often will use this one. And this is the formal definition of conservation of momentum, which is in an isolated system, meaning I have a system here, nothing's going in and out, meaning there is no exchange of forces, net external forces acting on my system, and because of that, I have no change in momentum. My total momentum in my system stays unchanged. So notice I have the keywords here in bold. It's isolated system, no net external force acting on the system, and resulting in your total momentum of your system to not change, okay? So a couple of ways to express this. You can have the change momentum equals to 0, which also means that the final momentum of your system is equal to the initial momentum of your system. Say two things collide, bam, momentum before the collision versus after the collision, momentum stays the same. Total momentum stays the same, okay? So let's take a look. I just talked about two object systems. Let's take a look at some quick examples. Conservation of momentum is awesome. So let's start with this one. Hey, look. So this guy is throwing some tennis balls in space. Let's take a look at what that looks like.
Or whether they're colliding with each other. Whether they're colliding with each other. It even works, in this case I put Velcro, it even works if these two stick together, the total momentum remains the same.
So in that example, you saw how after two tennis balls collide with each other, they kind of go off in their own directions. But then there's a specific one where they got stuck together, and after they got stuck together and they started moving, you notice they moved a lot slowly. So then you can see how the total momentum before and after the collision remain the same. Okay, so that's something that we are going to model. Let's say for a two-body system, okay, the change in momentum, let's say, of object 1 plus the change in momentum of object 2, let's say that's my total change in momentum. We know that the total change in momentum here is equal to 0, and we're talking to object system here. So then if I say move this guy to the other side, my other object, so that's negative change. I subtract change in momentum of mass 2 on both sides of my equation, I'm left with change of momentum of my mass 1 equals to the negative change of my momentum of the second mass. Hey, that's starting to look like something. Oops. And then we know that change of momentum is equivalent to some force acting on your object, where the force is exchanged, multiplied by the time that the two things were in contact with one another. So then we can rewrite this P1 and P2 as force acting on object 1 times the time that the force was in contact with object 1 equals to the negative force acting on the second object times the amount of time that force was acting on the second object. But then if the two objects are colliding, then the contact time that they have with one another is the same. So this delta T kind of goes away because it's the same on both sides of the equation. Hey, look what we have now. We have force acting on object 1 is equal to the negative force acting on object 2. Ooh, that's starting to sound like something we've heard before. And if you're thinking of Newton's third law, you are right. Newton's third law states that for every action, you have an equal and opposite reaction. So if I have an object pushing against this object's going to push with an equal and opposite force in the other direction. So this, my friends, is Newton's third law. And going by the definition of conservation, if there's no net external forces acting on my system, there can be internal forces. And if I have two objects colliding, that, in terms of the whole system, would be considered an internal force. So really, conservation of momentum, you can kind of think of it as Newton's third law. Let's take a look at an example. So here I have an astronaut, his name is Mark, and let's see what he's going to show us in space.
By object 1 onto object 2. However, there's a big disparity in the mass. Object 1 is a very light mass object. Object 2, myself, is a larger mass object. He's gonna throw the ball,
watch.
So, I'm going to try to make myself about the same shape as this ball. See how that works for us. And I'm going to apply that force.
Ooh.
You saw that force applied to the ball made it accelerate quite a bit. It really didn't accelerate me much at all. Newton's third law again, but this time we're going to use two similarly massed objects. Joe and I have about the same mass, so Joe, get into a ball. I'll do the same. I'm going to face you this way so that I don't throw you into something you can't see. Now I'm going to get into a ball behind Joe, and I'm going to apply a force to him.
Oh, that's sweet, yo. All right, so there we have a system. So you can see how here we have Joe, the guy in front, he went forward versus Mark, he went backwards. They both started with 0 momentum, okay? But remember, momentum is a vector. So after Joe after Mark pushed Joe, his momentum is forward, and Mark's momentum is now backwards. You can see if you add up the total momentum, it sums up to 0. So the total momentum before and after is the same, which was 0. Very interesting, hey? So now you're probably like, hey, well, it's really cool, okay, but how do I do all these problems? Help! So let's go back to the two-object system, all right? So we have the two-object system. We found out that the change momentum of number 1 is equal to change momentum number 2, and if you want to, we can always apply this to any collision problem or for conservation of momentum. So then here, if you want to write it out, we know change in momentum is just final momentum minus initial momentum, and we also know the momentum is mass times velocity here. So here I can write that the change in momentum of mass 1 is just m1 v1, and v I'm using as final velocity, minus m1 u1. U I use as initial velocity, just like in kinematics back in the IB data booklet. Okay, so then that is equal to negative, don't forget, oh, I forgot there's a negative sign here. Ooh. There I have the mass 2 times its final velocity minus mass 2 times its initial velocity. Okay, so that's one way you can use. What I prefer to use, and something that maybe would be better in terms of visualizing, is comparing before and after a collision. So oftentimes what I like to do is I like to draw a picture of what your system looks like before the collision. Draw a picture what it looks like after the collision. And we know that before the collision, the momentum is going to be the same as the final momentum after the collision, assuming no external forces are acting on any of those objects. And we know that initial momentum is just the sum of the momentum of both objects in your system. So then I can just say that is, let's just write it out, momentum initial of mass 1 plus momentum initial of mass 2 is equal to the momentum final of mass 1 plus the momentum final of mass 2. So if I write it all out, since momentum is mass times velocity, I have mass 1 times its initial velocity plus mass 2 times its initial velocity. That's equal to mass 2 times its final velocity plus mass 1 times its final velocity. I can swap that, whatever. So here is what I like to use when I deal with conservation of momentum problems, collisions, etc. I'm going to use that in my next video. Check out the example. Thank you for watching this video. Hopefully you learned something. Fat Mama Physics signing out.